Have you ever stopped and wondered what's really going on inside the apps on your phone? I mean, it seriously feels like magic, right? But it all starts with something, well, incredibly simple, just a switch. A switch that can only be on or off. Today, we're going to go on a journey, starting with that tiny little switch and zooming all the way out to the complex software that basically runs our world. It's an amazing story about how really simple rules can build unbelievable complexity. So, to kick things off, let's think about a really simple question. Imagine an app for school that tells you instantly if you passed your exam. How does it do that? How can a bunch of wires and circuits make a judgment call between pass and fail? Let's pull back the curtain on that little mystery. Okay, so here's a flowchart, a basic plan for a student exam system. The logic is super straightforward. If your score is over 40, you pass. If it's not, you fail. Simple enough for us. But here's the wild part. The computer running this logic, it has no idea what 40 is or what passing even means. Its entire universe is just two things, on and off. So if we want to understand how that pass-fail decision really happens, we've got to learn the machine's native language. It's time to zoom all the way in and start talking the language of on and off.
And that language is called binary code. It is the absolute bedrock of everything digital. Deep inside your computer, there are millions, actually billions, of microscopic switches. And the rule is simple. If a switch is off, we call that a 0. If it's on, we call it a 1. Every single thing you see on a screen, every letter, every color, every number is just a long, unique pattern of these zeros and ones.
Now this whole on-off system is what we call a digital signal, and it's totally different from an analog signal, like the sound waves from my voice. Analog signals are these continuous, flowing waves that can get all fuzzy with noise and just kind of fade out over long distances. But digital, oh, it's clean, it's precise. It's either a definite 0 or a definite 1. No maybe.
And you can really see that difference here, can't you? On the left, you've got that wavy, kind of messy analog signal, and on the right, the clean, blocky digital one. That high level is a 1, that's on, and that low level is a 0, that's off. There's no gray area, no in-between, which is exactly what a computer needs to make sure it doesn't make mistakes.
Okay, so we know computers speak in zeros and ones, but how do they actually, think with them? How do they make a choice? For that, we need to meet the real brains of the operation, the atomic decision makers. These tiny little decision makers are called logic gates. They're incredibly simple parts that act like tiny gatekeepers for information. All they do is take in one or two of our zeros and ones and then spit out a single 0 or 1 based on one very specific rule. Let's meet our first one. This is the AND gate, and it's a real stickler for the rules. The best way to think about it is like a high-security door with two different locks. If you want to get that door open, which means getting an output of 1, you have to unlock the first lock, and you have to unlock the second lock. One or the other? Nope, not good enough.
And its rule book, what we call a truth table, shows this perfectly. Just look at the options. It's only on that very last line, where input X is 1 and input Y is 1, that the output finally becomes a 1. Any other combination, the door stays shut. You get a 0.
Now on the flip side, we have a much more laid-back gatekeeper, the OR gate. This one is like a door with two doorbells. You can press the first doorbell, or you can press the second one. You could even press both at the same time. Any of those will get the door to open. And its truth table shows you just how forgiving it is. See? As long as either X or Y is a 1, the output is a 1. The only possible way to get a 0 to keep that door shut is if both inputs are 0. And then we have the simplest of them all, the NOT gate. People usually call it the inverter because that's literally all it does. It takes one input and just flips it to the exact opposite. It's kind of the rebel of the group. Its truth table is about as simple as it gets. A 1 goes in, a 0 comes out. A 0 goes in, a 1 comes out. And that's it. That's the whole story. So we have these three super simple decision makers, AND, OR, and NOT. And honestly, by themselves, they aren't all that impressive. But the real magic, the part where this all gets crazy powerful, is when we start hooking them up together. This is where we start to zoom back out and build some actual intelligence. Whoa, okay, now this looks complicated, right? But take a second and look closer. You can actually spot our little friends in there. There are some NOT gates flipping the signals, some AND gates checking if multiple things are true, and then an OR gate at the end making a final decision. This is the magic. By linking these simple, almost dumb little parts together in clever patterns, we can create circuits that do complex math and make really sophisticated choices. And because we can build these circuits to solve pretty much any logical problem, they have become the invisible foundation of our entire world. They're what make up computer memory. They help keep our data secure. They control everything from the robots in a factory to the medical devices in a hospital, all the way to the anti-lock brakes in your car. They're everywhere.
All right, we've gone from the humble on and off switch to logic gates to powerful circuits. Let's zoom out one last time to see how we organize all this raw power into a finished app, like that exam system we started with.
You can't just throw millions of logic gates in a pile and hope an app pops out. To build something useful, you need a blueprint, a recipe. And in the software world, that blueprint is called the Software Development Lifecycle, or SDLC for short.
This waterfall model is a really popular version of that plan. You can see why they call it that, right? It's a clear, step-by-step process where one phase flows right into the next, guiding developers from the very first idea all the way to a finished, working application. And the steps themselves just make sense. You start by defining the problem, what are we even trying to build here, and then you plan it out, you analyze what you need, and then you design the solution. It's only after all that planning that you actually start writing code, and then, of course, you test the heck out of it to make sure it works.
And right here, this is it. This is where it all connects. See that design phase? That's the exact moment when a human being creates the blueprint, the flowcharts, the logic, that will eventually get translated into all those combinations of logic gates we just learned about. Our pass-fail flowchart from the very beginning, it was born right here. This is the bridge between a human idea and the computer's world of zeros and ones.
So there you have it. The whole journey is really a story told in layers. We start with the basic physical language of on and off. We use that to build tiny decision makers called logic gates. We combine those gates into powerful circuits, and then we use a structured plan to organize everything into the software that we use every single day. When you think about it, it's just incredible that such immense complexity can grow from the simplest possible rules. It really makes you wonder, doesn't it? If today's most advanced AI and software are still built, at their very core, from these fundamental blocks of on and off, what's the next impossible problem that we're going to solve, just by figuring out a new way to arrange them? Thanks for watching.